Hello students and welcome to our discussion on the operations of functions. We were discussing how from the given two functions we can construct many new functions. Like given f1 and f2, I told you can find and form something like f1 plus f2 known as the sum of two functions f1 and f2. Similarly, I can find another new function known as the difference of f1 and f2 denoted by f1 minus f2. We can also talk about the product of two functions denoted by f1 into f2. And we can also talk about the division of two functions, or I can say quotient of f1 by f2 denoted by f1 divided by f2. And the definition of each of these functions, the way in which they were acting upon the inputs to deliver the outputs, was just dependent on the point-wise operation being carried out. If I talked about the sum of two functions, obviously the definition was one of the most exact ones, which was f1 plus f2 when applied to a certain x will be point-wise addition. f1 of x plus f2 of x for all x belonging to the domain of f1 and the domain of f2. Moving to the next new function which we studied was f1 minus f2. This function, when acted upon the input, behaved in a very obvious manner, which was point-wise subtraction happened, that is f1x minus f2x for all x belonging to again d1 intersection d2. The third operation dealt with the product or the point-wise product, as the name suggests. f1 into f2 of x was just the point-wise product. f1 of x into f2 of x, again for every x belonging to d1 intersection d2. And the last which we did in the last lecture was quotient of f1 by f2, and when this acted upon an input x, it behaved again in a point-wise division manner. And because I not just want x to lie in the domains of both f1 and f2, but I also wanted that x should not be one of those reals for which f2 of x is 0, because of which the domain happened to be d1 intersection d2 minus the collection of all those reals for which f2 of x is 0. Having understood these four operations on the functions useful to create even new and more functions, it's now turn to move on to the fifth very operation, which says multiplication of a scalar by a function. That means by multiplying a scalar to a given function, you can form another new function. Let's see what it is trying to say. Let f1 from d to r be a real function. By which I mean that this d is also a subset of the real line. If my f1 is a function from d to r and say alpha is any number, any real number is what it is, that means alpha belonging to r is any real number then the product of alpha, which is this real number, and f, the product of alpha and f denoted by alpha into f. This is the notation for denoting product of alpha and f. Yes, we have studied the product of two distinct functions, but we have not studied the product of a function and a scalar. By a scalar, I mean a constant inside the real line. What do I mean by multiplying a constant with a real function? That is, it will be clear by the way this is defined as. It is defined as when this function acts upon the inputs, what does it do is, this f1 which is already present, this f1 acts upon the input, and once this real number is obtained, because f1 of x is inside the real line for every x inside D1, you multiply this real number by the real number alpha. And this is valid for every x in D1. Because for every x inside the domain of f1, f1 of x is a real number. And alpha is already a real number. Product of two real numbers will always be a real number, and that is why the only point of concern is that f1 of x should be real, because alpha is already real. And f1 of x will be real only when x belongs to the domain of f1, that is D1, and therefore this particular function, which is known as multiplication of a scalar by a function or real function, is again a function behaving in this manner and denoted by alpha into f. Once we have understood this very new operation regarding the operations concerning with the real functions, it's now time to move on to the last operation. Of course, concerning the domain of alpha into f, there was no hassle, because this expression of alpha into f being defined as alpha f into x or applied to x was alpha times f1 of x. There was absolutely no confusion regarding the x which are allowed to come and sit in front of alpha f1. Because for every x in the domain of f1, the same x's were allowed entry inside alpha f1, provided alpha is a real number. Moving to the last operation which is valid for real functions, we have reciprocal of a function. By the reciprocal, when we understood reciprocal function, I told you corresponding to every non-zero real number, you have a reciprocal which is again a real number. Take 2, its reciprocal is 1 by 2. Take minus 4, its reciprocal is 1 upon minus 4, which is minus 1 upon 4. And that means every non-zero real number has its reciprocal, and the reciprocal is nothing but 1 upon that real number. Similarly, if I wish to talk about the reciprocal of functions, I want corresponding to a function f which is non-zero, I wish that its reciprocal comes out to be something very intuitive, which is 1 upon that function. And that is what is the definition of the reciprocal of a function operation. Let f from D to R be a real function. Then reciprocal of f denoted by one upon f and defined for f non-zero as, I already told you, f has to be non-zero for 1 by f to occur. And therefore, for f non-zero, I can define my reciprocal 1 by f as, when this 1 by f is applied on the input x, what you get is 1 upon f of x. Now, if I wish that 1 upon f of x is a real number, 1 is already real, I just want fx to be real. And fx is real for all those x which are coming from the domain of f, which is D. That means fx is real for all x belonging to the domain of f, which is D. But one upon fx is not real for those x for which fx is 0. Because if for some x fx is 0, then 1 by fx for that x becomes 1 by 0, which is not defined. And that is why I not just want x to come from the domain of f so that my fx is real, but I want x to be those members of the set D for which f is not just real but a non-zero real. Because if for any x inside D, my fx will be real, for that particular x, 1 by fx will not be real. And so for 1 by fx to be real, I not just want my x to come from the domain of f, but I want my x to come from those members of the domain of f for which fx is non-zero. And therefore 1 by fx is going to deliver you real values for those x's as inputs which are coming from the set D minus the set of all those x for which fx is 0. Yes, I want x to come from domain, otherwise fx will not be real. But I also want my fx to be non-zero real, because of which I want x to come from D minus the set of all those x for which my fx is 0. And this is what decides the domain of the function 1 by f. This completes my operations on the real functions topic. We discussed about several operations on real functions: the addition, subtraction, product, quotient, multiplication of a scalar by a function, and in the end, the reciprocal of that function. It's now time to move on from the operations of functions, which basically helped us in constructing new functions. What did operations do? These operations basically helped us to bind functions, more than one function, to bind them and create new functions. I can bind them through the operation of addition, or bind them through the operation of subtraction, or through product, or through quotient, or through reciprocals. Now if I just make one small point, we all know from the operations that f into g, if f and g are two real functions with their specific domains d1 and d2, suppose, then f into g of x is fx into gx. And you know x should come from where? This x should come from the domain of f as well as domain of g, say d1 and d2. And therefore x should come from d1 intersection d2 for f into g of x to be real. Now because I know this already, what if I take my g to be equal to f? What I get is, I get f into f of x, or I can say f square of x. And by definition, I know what it is. It is pointwise product fx into fx, which is nothing but fx whole square. If I try and do that with three functions, the same function f multiplied thrice is nothing but denoted by f cube x, because f is being multiplied 3 times. And this by definition is nothing but fx into fx into fx. Pointwise product, which is nothing but fx cube. Thus, for every n belonging to this particular set, I can have fn of x, which is nothing but f into f. That means the product of f taken with itself n times. And by definition, you will have f of x into f of x into f of x n times, giving you f of x to the power n. This is what is the meaning of, or basically a significance or use of, the operation of product. I can multiply and have a self multiplication of a function with itself coming up as another kind of an operation. Once I have one function, I can multiply that function with itself any number of times, finite number of times, and I am going to keep on obtaining new functions. Have one f, multiply it twice, get a new function f square. Have one f, multiply it thrice, get a new function f cube. In this way, this operation of self-multiplication, which actually is a deduction from the operation of product, is also used in forming, framing and bringing up new functions. From one function, we were able to create in this way new functions, some more functions. This is where I end my concepts about operations on functions. Once we have learned how to bind functions together, how to create new functions from the already existing functions, we are now in the zone to understand the different kinds of functions. What do I mean by kinds of functions? Before I move on to what all kinds do functions possess, in which category do functions actually lie, is going to be depicted by the topic kinds of functions. Before that, let us quickly revise the functions that we have done up till now. The first function we dealt with was the constant function. Constant function looked something like this. Some k constant was sitting over here, x and y axis over here, by a line parallel to x axis was the depiction of the constant function. The next function we did was the identity function. Which looked like this. You had your x-axis, your y-axis and a straight line inclined at an angle of 45 degrees with the positive direction of x-axis. The third function we dealt with was the modulus function, and that function looked and had a V-shaped structure. Next function which we dealt with was the greatest integer function. And how did that look like? Well, it had steps involved. From 0 to 1, the answer was 1, and I had in picture such a scenario. And this continued. This was what was my greatest integer function. If I move on to understanding what were the other functions which I did and how were they represented in the form of graphs, the next continuing in the list after the fourth number, I have the least integer function or the smallest integer function. And that looked like what? Well, from 0 to 1, the least integer, as like here, it was, the least integer happened to be 1, and therefore I had well, this resembles the greatest integer function already. In the greatest integer function, we had that greatest integer which is smaller to my real number. And so, this function actually says that from 0 to 1, if the answers are coming out to be 1, it is actually the least integer greater than the real numbers lying between 0 and 1, and therefore this was actually the graph not of the greatest integer function, but in fact the least integer function. Because that was what the definition was concerning to the least integer. Now moving on to understanding the greatest integer, I am interested in finding out the greatest integer which is less than a real number. The greatest integer less than a real number means from 0 to 1, the answer is going to come out to be 0. But at 1, I'll have a blank. Then from 1 to 2, this is the scenario, and so on. This is what is the graph of the greatest integer function. After which we went to understanding the fractional part function. The graph of the fractional part looked like this. Moving to the signum function, I had in picture a line passing through the 1 and another line passing through -1 with 0, 0 ordered pair also included. Having exponential function as the next one, either it looked like this or it looked like this. Similarly, we did logarithmic functions, which looked like what? It either looked like this or it looked like what? As you move towards right, this is approaching to 0. So, as you approach towards 0, what happens? The values keep on increasing, because of which this happened to be your next graph. These two standing for the cases of exponential and logarithmic function depending upon the base A's range, whether A is between 0 and 1 or A is greater than 1. After this, we did the reciprocal function, square function, cube root and square root functions. Having dealt with so many functions till now, it is time to understand the topic kinds of functions. Why? Because we will be able to then classify all of this huge variety of functions into distinct classifications and kinds. Coming first in the category is the first kind of function known as one-one function, also known as injective mapping. What do I mean by a 1-1 function? This says if distinct elements of set A have distinct images in set B is when my function is called a 1-1 function, provided what is A and B? F is a function from A to B. And then F is called a 1-1 function. That means when F is actually sitting as a function with domain A and codomain B, and distinct members of set A are getting mapped to distinct members of set B, I will declare my function to be a 1-1 function. If I, before moving to theory once more, let me look at these functions and see if I have 1-1 functions in picture or not. Starting with the first function, I want distinct members of the domain to have distinct images in the codomain. Here, this member is in the domain, this member again is in the domain, and these two are distinct. Suppose I mark them as x1 and x2. Corresponding to x1 I am getting the image k, and corresponding to x2 also I am getting the image as k. That means distinct members of the domain do not have distinct images, they have the same image, and therefore constant function is not a 1-1 function. If I move on to the next function, which is identity function, the depiction of this function speaks that yes, corresponding to any number you take, you will have that same number as the image. You take any element in the domain, the same element happens to be the image in the codomain. So if you take two distinct members in the domain, the same two distinct members will come as the image, and therefore if the two members from set A are distinct, obviously their images will also be distinct because they are the same members under the identity function. And that is why yes, identity function, yes, is very much a 1-1 function when constant function was not a 1-1 function. Moving to the next function, I already have that modulus of 1 is 1 and modulus of -1 is also 1. That means 1 and -1 are two distinct members, but their images under the mod function are the same, and that is why even this is not a 1-1 function. Talking about the least integer function, yes, corresponding to every member between 0 and 1, I have the same image as 1. That means if I take any two distinct members in the interval 0-1, I have their images as the same number 1, because of which distinct members of the domain are not getting mapped to distinct members in the codomain, and therefore even this is not a 1-1 function. Similarly, greatest integer function is again not a 1-1 function, exact same argument. The fractional part function is what? Is this a 1-1 function? Well, if I start observing, yes, corresponding to every real number in the domain you pick up, you obtain a distinct image. But are you getting that? Well, if I just concentrate on this portion of the domain, it is covering all the real numbers given over here from 0 to 1. And considering this part of the domain, again the real numbers as images are getting repeated. That means over here if I take a number x1 and over here if I take a number x2, there do exist x1 and x2 which are not same, but their images are same. That is what the graph is depicting. And that is why no, fractional part is not a 1-1 function, because there do exist a pair of numbers x1 and x2 such that their images are exactly the same. The next one is the signum function, which is very evidently not a 1-1 function, because corresponding to these two distinct numbers, their images are exactly the same, which is 1, because of which this is not a 1-1 function again. The next function is the exponential function, which is very clearly a 1-1 function. Pick up any number on the domain, you have a distinct image in the codomain. No two members in the domain give you the same image in the codomain, because of which exponential function is a 1-1 function. Similarly, logarithmic function is also very much a 1-1 function. This is what is the meaning of 1-1 function, that distinct members in the domain should possess distinct images in the codomain. Even if there are two members in the domain corresponding to which the images are exactly the same, I am in a position to declare that that function is not at all a 1-to-1 or 1-1 or injective function. The mathematical definition says that f is a 1-1 function provided this holds. That is, whenever x1, x2 are two members in the domain A such that x1 is not equal to x2, this means x1 and x2 are distinct, in this case, whenever you have x1 is not equal to x2 in the domain, it should imply that their images in the codomain are also not equal. That is, their images are distinct. If x1 and x2 are distinct, their images should also be distinct. For any x1, x2 distinct, their images should be distinct. The working rule for finding out whether a function is 1-1 or not is very simple and intuitive. The working rule says that firstly, if f is a function and any horizontal line any horizontal line passes through or intersects the graph of f exactly once, only then f is 1-1. That means once you have the graph of f drawn with you, you can pick up any horizontal line that you want and make it pass through the graph. If every horizontal line, that is, any you pick up, passes through the graph or intersects the graph at exactly one point, you declare that function to be 1, 1. If you don't believe me, we can use this test and actually attain the same answers as we did when we checked our functions to be 1, 1 or not. If you remember, I presented before you the graph of the identity function. Make any horizontal line pass through the graph. Any horizontal line passes through the graph at most once. That means, yes, this passes through the graph at exactly one point. Passes through the graph at exactly one point. In fact, each horizontal line passes through the graph exactly once. Either it doesn't pass at all, like this, or if it passes exactly once, which means fx equals x, that is the identity function, is a one-to-one function. I can classify my identity function to lie in the category of 1, 1 functions. But on the other hand, if I talk about fx equals modulus of x, the graph falls to be this. Pick any horizontal line like this. It is intersecting the graph at two distinct points. But my definition and test said that it should intersect the graph exactly once, not at all more than once. And because there is one horizontal line, in fact there are many horizontal lines, if you keep on drawing, I just needed one horizontal line for my test to fail for modulus function. I could find one horizontal line which was intersecting the graph not exactly once, in fact more than once, that is twice, and therefore fx equals mod x is not a one-to-one function. If you carefully observe, there is a term known as monotonic also related to the test of actually testing whether a function is 1, 1 or not. What do I mean by monotonic? That is what is my second description of the test. It says, if f is a monotonic function, that is, either f is increasing or decreasing throughout its domain, then I say, and only then, this is an if and only if condition, f is 1 to 1. By monotonic, I mean f should be always increasing throughout its domain or always decreasing throughout its domain. If you look at the identity function, it is increasing throughout its domain. If x1 is less than x2, fx1 is less than fx2. That means your function is increasing throughout. That is, whenever x1 is less than x2, belonging to the domain of f, it should imply that fx1 is less than fx2. This is what is the meaning of increasing. Or if x1 is less than x2, it implies fx1 is greater than fx2. This implies the function is decreasing throughout. This should be true for every x1, x2. in the domain of the function f. Thus, either the function should be increasing throughout or the function should be decreasing throughout. I will have that my function is 1 to 1. I call such functions to be monotonic. So that means I want my function to be either increasing throughout or I want my function to be decreasing throughout. If I talk about an example, what kind of a function do you think this is? This is the exponential function which is decreasing throughout. For this value of x, this is the output. For this value of x, you have a reduced output. That means as you are moving on the number line, the value of fx is decreasing and decreasing, thereby giving you a decreasing function throughout the domain, which is the collection of all reals. In fact, if you apply test number 1 over here, you make any horizontal line pass through the function, it will be intersecting the graph at exactly one point. So either you use the test of f being monotonic throughout, that means either increasing throughout or decreasing throughout, or you use the horizontal line test, you have that f is 1, 1 function. Whereas if you take your greatest integer or least integer functions, suppose I take this one, then in this case, yes, you can find the function to be increasing, but it is not increasing throughout because there are points corresponding to which you have the same image. In fact, if you use your horizontal line test, if you make a horizontal line pass through this particular segment, you will have this horizontal line is passing through this segment at so many points. It is intersecting the graph at so many points. It is not intersecting at exactly one point. Because of which not just this test but this test also fails, and therefore it's not a 1, 1 function. These are the two tests which we use to actually find out and conclude whether a function is 1, 1 or not. We are going to move on and study the next kind of function in the next lecture. Till then, keep your grasping power on these concepts very, very firm. Meet you next time. Take care.